our next speaker is writing a book. And it's a good book. I've read what's in it so far. And he's reading a lot of books, probably more good books than most of us have read in our lifetime, in order to research and come up with material for this book. And so in order to just get some of that radiating ideation coming off of him and soak it up, because it's not all going to make it into a book, I invited him to speak. So our next speaker is Tellman, and please take it away. So I've been writing a book. And the way that I have been explaining this book lately is that it tries to put words to what most experienced engineers already know. And this is useful because we have the capacity to understand a thing and still struggle to explain it. And this is what Michael Polanyi calls passive knowledge, something that we only understand as part of something else. I'm standing in front of you here speaking. I know how to speak. But as I'm speaking, I'm not focusing on the physical act of speech. I'm focusing on the words. If you stopped me and asked me to sort of pull back and explain to you what are my vocal cords doing right now, I'd be at a loss, right? I haven't had reason to think about that deliberately. And this is okay. Tacit knowledge accounts for most of how we understand the world, because it takes a lot of effort to explicitly understand a thing. But Polanyi tells us that tacit knowledge only works, only suffices, as long as the intuition it gives us doesn't sort of steer us wrong. Once it does, we have to look at the thing directly. We have to understand it explicitly. And there's some things that we understand tacitly in software. We acknowledge that names are one of the few hard problems, but we spend almost no time actually studying them directly. We seem to just assume that if we write enough code, we'll stop being bad at them. Likewise, we clearly work with these things called abstractions, but I've seen countless conversations between engineers where it became clear halfway through that they had very different understandings of what this word meant. And this might even be okay if it weren't for the fact that we write software that does fail, and those failures are due to names and abstractions, whatever that may be. And so we can't continue to look past these things. We have to look at them head on, even if it is a little labor-intensive, even if it is a bit difficult to wrap our head around them. And so that's what my book is about. I'm trying to go and provide a vocabulary. I'm trying to provide a framework for judging these things because it's time. We need it. And so elsewhere I've talked and written about names and abstractions, and I don't have time here to speak about all that. But the big takeaway for abstractions is that abstraction is treating things which are different as equivalent. So we have here the same tree pictured over 4 different seasons. And I say it's the same tree, even though there's some pretty big differences, right? It's covered in snow or not. It has leaves or not. The leaves are green or not. And despite that, the identity carries through. We agree that this is the same tree. And so what we're tacitly saying there, what we are presuming is that those things are incidental to its identity. They don't matter. A leaf falling doesn't force us to reevaluate everything we knew about that tree. And that's crucial because the world around us is constantly changing and we do not have the time or energy to constantly reevaluate everything we know every time that happens. And so abstraction is key to how we understand the world around us, as well as how we write software. But if we acknowledge that abstraction is fundamentally the act of ignoring things, ignoring most things even, we have to acknowledge that we can't just say whether an abstraction is good in some sort of absolute sense. We judge abstractions within the context in which they're intended to be used, because anything that we ignore might steer us wrong in a particular situation. I care a great deal about whether or not a tree has leaves if I run a lawn care service. I care a great deal about whether or not they're going to fall. Those are central to the tree's identity for me. And so when we talk about composition, which is taking abstractions and placing them next to each other, we can see this as sort of beginning to define this context, right? These different pieces of software placed next to each other define each other's environment. And so we begin to actually be able to judge these things in a concrete way, rather than just talk in the abstract about the act of judgment. And so I want to talk a little bit about composition, right? And we know composition generally from our sort of grade school math books as taking two functions and making one function. And this clearly plays a part, right? But it is not the end of the story, because if we go and we put together a bunch of pure functions and yield one large, monolithic pure function, that's still passive, right? It does not interact with this environment. It needs something else to actually invoke it. And so we can't just talk about functions and sort of leave it at that. What we're trying to create is something that has an active relationship with the world around it. And so what we're trying to construct is a process, something which pulls in data, which transforms the data, and then pushes that result elsewhere so someone else knows about it. And I'm defining a process to be, something which is not necessarily what we would call a West process these days. It's something a little bit more specific. It is something that operates sequentially. All of the actions that it takes are ordered with respect to each other. It has execution isolation, which means that its actions are ordered with respect to each other, but not with respect to things that are going on outside of it. It also has data isolation. There are things that the process and only that process can see. And so the most common example of this that we would work with day to day is a thread. But we could also find these same properties in a linear chain of callbacks. We could also find it in early Unix processes which didn't have threads. We could also see it in Carl Hewitt's actor model and resultant processes in Erlang. We could also see it in the original iteration of objects in Smalltalk, where objects originally communicated via asynchronous message passing, though in later versions of Smalltalk that turned into synchronous RPC, which became something more akin to the OOP that we're familiar with. And so this is an incredibly common concept. Doesn't always share the same name, but it is found everywhere in the even early history of software. And the reason for this is that it processes the smallest unit of code, which has value on its own. It can actually do a thing. It doesn't need to be combined with something else to be useful. But in order for this to be true, it has to do all three. It has to pull in data, it has to transform it, it has to push. And just to kind of inform your intuition for this, I want to talk about a few Unix utilities which don't do all three, and sort of look at how they're not particularly useful when used in isolation. So the yes utility, reproduced here in Clojure, will go and repeatedly print out y new line over and over again. This is valuable when placed upstream of a process which has interactive prompts that we want to blindly agree to. And so this can be useful, but clearly has no value on its own. It's only useful when used in concert with this other thing that has interactive prompts. Likewise, we can see dev null as something which only pulls in data and then drops it on the floor. Again, this is useful when placed downstream of something which has an effect beside what it's printing out to standard out. And we want that effect, but want to ignore what it's actually printing. And so again, useful, but not on its own. Cat is something which, given a list of file names, will go and fetch the contents of those files and print it to standard out. This is pulling in data, it's printing data, but it's not doing any transformation, it's just sort of passing it along, unchanged. And so this is valuable because a lot of Unix utilities don't read from the file system, right? They read from standard in. And so cat is a bridge to that file system. Likewise, netcat is a bridge to the network, right? This has value because it bridges two things together, but on its own, it just kind of hangs there, it does nothing. Lastly, we can think of a slightly more high-fidelity reproduction of the yes utility. Because yes doesn't just print out y, it can also print out any expletive that we provide. If we wanted to have it print out n, or yes, or something like that. And so we can see this kind of as a transformation, right? We're providing this initial parameter when we instantiate this utility, and it's transforming it into an infinite recurrence of itself. So this is slightly more useful, right? There is some sort of transformation going on here, but the thing that I'll observe is that generally the usefulness of the output is commensurate with how complex the inputs are, right? If what we're doing is just giving it what is literally at our fingertips when we run this utility, then it's just going to tell us a variation of what we already know. And so in general, we want to not have bounds to that, and by limiting ourselves to only what we have when we instantiate a process does place great bounds on that. And so there are a few counterexamples you could name, which are largely from the domain of mathematics, pseudo-random number generators, fractal geometry. Those take small initial values and yield large outputs. But I will point out that neither of those things are valuable on their own. We don't generate randomish numbers just for the sake of it. We don't generate fractal images and then not look at it, right? We do these things because they are useful in place upstream of something else. And And so again, in order for this to be sort of standalone, to be useful on its own, it has to do all three. So I said that processes have data isolation, right? There's data that they and only they can see. And this is true, but consider a case where you start up a process, we hand it some initial values, and it just has a bunch of immutable values floating around. We can certainly compute things about those, right? But what we can't do is share it with the rest of the world. Communication occurs via shared mutable references, right? In order for us to get data, someone has to update a reference that we can see with new data that we need. In order for us to share data with somebody else, we need to do the same. And so mutation is a necessity. Otherwise, we're just sort of raising the ambient temperature of the room. But we want to limit mutation wherever possible, because if we have some sort of data structure which allows for mutation, and we hand it to some function, and unbeknownst it shares it with some other process, we've just added an edge to our system, right? We have now created this linkage, which we probably don't want, right? Certainly, if it wasn't something we could have predicted, it's going to make it very hard for us to reason about how the system works. And so we want to use mutation where necessary, but nowhere else. Likewise, I said that processes have execution isolation, right? They are ordered with respect to their own actions, but are not ordered with respect to anything else outside of it. This is also only partially true, because sometimes we need data from the outside of process, and that means we have to wait for it, right? Consider what happens if we are reading from the file system. We say, I would like to have the first, block of data from this file, and then we have no choice but to just wait until the file system provides us with that, right? We can't make forward progress without this data. And this is fine, right? This is a very simplistic idea of how a file read happens, but what happens if it takes too long? We can't simply just say, gosh, I guess the amorphous file system isn't working. We have to reason about what's going on inside of it. And unfortunately, the truth is a little bit more complicated. This, by the way, is a hugely simplified view, but at the very least, we're passing through a cache. And if we have a cache miss, we go to the IO scheduler, which will go and try to prioritize and deduplicate our reads. It'll then pass it along to the disk controller, which is an external piece of hardware that talks to the actual storage medium, which at the end of the day is actually the thing that limits what sort of write capacity or read capacity that we have. And so in order for us to reason about why are we slow, we can't just say, gosh, I don't know, the file system's slow. Right? We have to actually start to look at these individual pieces and understand who's waiting on who, right? Who is active here and who's just passively waiting for the next guy. And worse yet, we can't just do this, because we also have to think about who else is contending with us for the finite resources of this file system. And so in order to debug why is this slow, we have to hold all of this in our head. And by and large, we are not able to hold this in our head, right? We can try, but we're going to struggle a great deal. And we certainly don't want to do this very often if we have to. And so we shouldn't. But what we can't just say is, we need this to be fast so that we don't have to think very hard, right? The only control we have is to not care when things are slow. We need to allow for things to be slow, because that allows us to be incurious, right? But not only that, we need to expect that our low expectations are still going to be disappointing. We need to have timeouts. We need to have code paths that handle those failure modes. This is the only way that we're able to consider our process in isolation, is we make it not terminally dependent on something that's going on outside. And so this may seem like I'm advocating for you to give up. Because the reason that we do this job, the reason that we're good at this job, is because we are preternaturally able to hold a lot of moving parts in our head, right? This is something that we are proud of making. And certainly we write specs where we say this needs to be fast. It needs to never go over some sort of threshold, right? We want this to be a reliably fast system. But the problem is that if we can't hold the system in our head, it's too large, we are going to get things wrong. The system will grow slow and flaky despite our best efforts. And so the only way that we can actually guarantee this property is to radically simplify the system. And in practice, the existing foundation that we build atop, the operating systems, all this sort of accumulated sort of software over the last half decade, it's still too complicated, right? Radical simplification is not within reach. And so we have to just have low expectations. So I want to give you a little bit more of a practical understanding of a process. So I want to run through a few simplified real-world examples. The simplest example of a process is something that we all know, a REPL. A REPL pulls in data from outside the process, which is a code form. It transforms that code form into its evaluated result. It then pushes that result out via print, and it does it all over again. And so, simple, right? Very easy to reason about. does all three things. And looking at this, we would reasonably expect that most of the time we're going to be blocking on read. Because eval and print run at computer time scales, while read is waiting for our big dumb fingers to actually type something in, right? But it's easy to come up with counterexamples of this. We could, for instance, ask the REPL to sum all the numbers between 1 and a billion. And at that point, we can probably type in a second command before it's done evaluating the first. Likewise, we could ask it to print out all the numbers between 1 and a billion, which means that whatever is downstream of our REPL is going to have to go and present all that stuff before we actually can type in a new command, which is even less likely, right? Emacs doesn't like this very much, it turns out. And so the thing that you need to realize is that there needs to be a little bit of coordination on either end of this, right? When we pull, we are letting the outside world know that we are ready for more data. They are not just throwing it over the fence. We are allowing them to send us something. Likewise, when we push, the outside world is allowing us to send them something. And so when I talk about push and pull, I do not mean that as a unidirectional bit of communication. What I mean is that on net, the flow of data is in one direction or the other. Likewise, let's consider an HTTP handler. We take an HTTP request, we transform the request into a database query, we execute the query, and then we take the query result and turn it back into a response. Right? This is the idealized version of Clojure as a back-end sort of tool. And I want to break down each of the individual steps that are involved here. First, outside of our handler, the web server is going to pull in the bytes off the wire that represent the request. Then it's going to transform that into the ring request that we all know and love. It will then invoke our handler. It will then transform that request into a database query. It will then pull the result of that query from the database. And I'm sort of smoothing over the fact that we're pushing stuff, because on net we assume that there's more data coming back than we're sending. We then transform that result into the ring response, and then we return this from our handler. Outside of our handler, we then transform that ring response into the encoded bytes. And then finally, we push it back to the client. And so this is a fair bit more complicated than the REPL, right? There's more stuff going on. There's not this sort of very clear cycling between pull, transform, push. And this is true for most real-world processes, right? They're not usually that simple. But the more important thing that I want to point out here is that we are not going and defining the boundaries of our process when we write a handler. Right? There's stuff going on outside of the edges that we need to reason about if we want to reason about the operational qualities of our software. And so a framework is often defined as code which calls us, as opposed to a library, which is code that we call, right? And when you're operating in a framework, that means you have to actually understand kind of what it's doing to be able to reason about what's going on in production. Lastly, I want to talk about a front-end application, a very simple one, which has a single button that's marked refresh, and some little base data, and when you click on the button, it'll go and query some service, and when the service returns, it'll update the DOM to reflect the new information. So the first thing that I want to point out here is that this is not a process, because you can click the button, and while we are going and querying the backend service, you can click the button again. And both of these queries will be going on concurrently, which means that they are not ordered with respect to each other. So this is actually a way of spawning processes, where each process will go and make a query and update the DOM and then disappear. But we might recognize that it's not very valuable to allow people to go and sort of spam this button and thereby spam our backend process. So maybe we want to stop that, right? So we add a little bit of state. We have an atom that marks whether or not we are refreshing, and then each time they click, we check whether or not there's already an in-flight request. And if so, we just kind of ignore what they're doing, right? So they can go and click the button, but we don't have to pay attention. Conversely, we might want to do something a little bit more explicit. We might say, when you click on this, we're going to disable this. Maybe put a little spinner there or something like that that says your click is not welcome. And then again, we enable it when we're done. These are both valid strategies, as is queuing up all the buttons to be, or all the clicks to be executed serially, as is any other sort of strategy you might come up with. There's debouncing, there's everything. But at the end of the day, we have to acknowledge that sometimes the external demands or external supply is not going to match up with what we want it to be. Right? So at the boundaries, we have neighbors that don't behave the way that we would wish them to. And we have to come up with strategies to deal with that. And that strategy, as a whole, is called an execution model. And I want to call it specifically queues, because queues are a very common and very useful way to connect different processes. Right? They allow for us to go and communicate when there is supply in response to the demand, and vice versa. But in the most naive use case of this, where a queue is allowed to exert back pressure, and we just wait indefinitely for it to allow us to make forward progress, we are now bought into our neighbor's execution model, right? Their choices become our choices. And so occasionally you will hear people talk about queues as this great thing which allow us to reason about different parts of our system in isolation. And this is not true. Because if these things are joined together, if they're in a suicide pact with each other to wait until the end of time for the file system to come back, then we have to reason about them as a single unit. We have to hold that pair of processes, or that entire set of processes, in our head to understand what's going on. The thing that allows us to reason about our code in motion is low expectations, timeouts, and explicit failure modes. That is what gives us separation of concerns. So when we talk about actually putting a process together, I want to consider the REPL layer. Let's assume that we're a little bit more configurable. When we start our REPL process, we provide functions that do the read and the eval and the print. So it's pretty evident that we want these to all be passed in, right? They have to be combined into a single unit, but we don't want to do this too early. There's no reason to have this function take a read-eval or an eval-print parameter, because these are wholly separate in what they're performing. We might want to read from the console. We might want to read from the network. We might want to print to the browser, right? These are all separable concerns to the actual act of evaluation. And more generally, the reason why these things are separate, right, why we only want to bind them together at the last possible minute, is because they're solving fundamentally different problems. Push and pull, these phases, are responsible for the operational aspects of our code, for our code in motion, right? The transform phase describes the value that the process is providing. And it's something that we can reason about fairly well with respect to the code at rest. So, to illustrate this, I want to talk a little bit about sort. According to the first sentence of the docstring for sort, it returns a sorted sequence of the item in call. The way it actually accomplishes this is to take a call, turn it into a sequence, realize the entire sequence, turn it into an array, and then perform an in-place sort. Of course, that's not the whole story, right? Because if we go and give it something too large, then it will simply run out of memory. Because it assumes, naively, that whatever we give it will fit in memory. Note that the docstring does not tell us not to do this, right? This is just assume that we know not to do this, you fool. But this is not intrinsic to the act of sorting, right? And to see this, let's look at the GNU sort utility. GNU sort will take a large stream of data. It will go and take in a chunk of that data. It will sort that chunk, spill that chunk to disk, and then repeat until it has exhausted the input, at which point it will go and take each of the chunks and merge sort them together. So this is more complex, right? Before we were talking about just transforming data, now we have this push and this transform and this, or pull and the transform and push, and then we have the subsequent pull and push that's doing the merge sort. This is fairly complex, right? There are more moving parts here. But it is robust. It is taking something which was an assumption and turning it into an invariant. And the reason that we have these invariants is not just because it makes our life easier, right? If we have an assumption, that becomes everyone else's problem, right? It makes the rest of our system less robust. We want to go and not leak these assumptions out, if we can possibly avoid it. And so the pull phase is responsible for exactly that. It makes sure that the data is of the appropriate size and shape. It enforces these invariants so that the transform step gets to be naive, gets to go and have this simplistic docstring that does not capture these sorts of failure modes. It also has to define what happens when the data is not available or not available soon enough. What the pull phase does not do is simply provide a lazy sequence. Because a lazy sequence is something that can go and trip up sort. It is something that can go and fail because suddenly the disk is unavailable or the network connection is closed. If we go and just sort of pass this in, our transform phase, this thing which is meant to be sort of pure, which is meant to be related to just the data as it is, not our sort of code in motion, can throw an exception at any point. And so this is something that people do a lot. I have done this a lot. And so I'm not trying to call you all bad people. In many cases, this is appropriate if you are only doing this as a one-off and you know exactly how big your data set is, right? It's also valid if you have like a config file, which will never get too big anyways. But in the most general case, if you want your code to be general, if you want it to be reusable, if you want the person who has your job 3 years from now not to hate you, you need to go and actually think about these operational qualities. You need to put guards at either end of your process. The transform phase turns well-shaped data, data which has been validated, into other well-shaped data. And there are three things we can do today. We can accrete data. We can take two pieces of data and combine them. We can reduce data. We can take data that we have and turn it into something less than its current form. And we can reshape data, which is neither grow it nor shrink it, but turn it into a different representation, which is advantageous for what we want to do. We accrete data when we don't have enough data to make forward progress, or when we would like to have more data to sort of operate on as a chunk. We reduce data when differences in our input don't matter. If we sum together a list of numbers, we are saying that any possible list which yields this particular sum is equivalent. We are blind to their differences, right? It doesn't matter. And so this is abstraction, right? This is treating things which are different as equivalent. And a common example of this is from the field of statistics. This is called Anscombe's quartet. These are 4 different data sets which share a bunch of really common metrics. They have the same mean and variance and correlation between the two axes and a few others that I forget. And so by using these metrics, by throwing away all the other data, what we're saying is, these all look the same to us. We are blind to the differences, right? And sometimes that's true, more often it's not. But this is an incredibly thorny issue, right? And again, I've talked about this elsewhere. Abstraction is something that I've talked about at length, and it's important because reduction is often the valuable part of our code, right? We accrete value, our data, so that we can go and do some sort of reduction to it. We reshape data so that we can actually go and do these sorts of reductions, because that is pulling out one insight among many. And so yeah, when we reshape data, we do this to make it easier for us to accrete or reduce. This is not abstraction, right? We are taking these different things and we're putting them into a particular representation because that representation is different in a way that we care about, right? We care about differences. So consider a database versus a flat file, where they both contain the same data, right? These are equivalent in the same way that all Turing complete languages are equivalent, which is to say, not in a way which matters in an engineering context, right? It might be some sort of clever little mathematical isomorphism, but that is not our day-to-day sort of job. Likewise, we can go and represent a map as an associative list, but most of the time we don't, because the map gives us affordances that we like, right? We like random access, we like random rect, we like random reads. And so we do this to set ourselves up to be more successful down the road, right? Because this allows us to do things that we couldn't do at all, or we couldn't do in a reasonable amount of time. And reshaping should always be a separate operation. It should be a function unto itself. If our function requires a set to be able to do something efficiently, we should not take some collection and coerce it to a set, right? We should be loud and proud about the fact that this is what we need, because it means that the people who are using our code know what we need to be successful and can reason about the trade-offs of coercing data early, reusing that coerced representation, all these other sorts of things, right? We should not do this silently for other people's benefit. Likewise, if we can, we should keep the accrete and reduce steps separate. This is not always possible. If we're going and taking a list of values and putting it into a set, we are accreting these values, but we're also losing information about the ordering of the values and how many duplicates there are. And so this just kind of both happens at once, and that's fine. But if we can get away with it, we should keep them separate, because this code doesn't really relate to each other very often, right? We can't actually go and reuse them, and by keeping them separate, we leave more degrees of freedom open for ourselves. What we're transforming data into is a description of the effects that we want to have. What is the next pull? What is the next push? And often, this is pretty straightforward. What we're giving is a description of the data we want to push. When we call printline, we are getting a literal description of the data we want printline to print, plus a new line. And even in a more complex example, where we have, say, an HTTP request, this is still a fairly literal description of what we're sending on the wire, right? It has to go through a sort of little transformation, but there's nothing here that doesn't have an exact correlate in what we're sending to the other server. But sometimes there are things that don't fit into that sort of category, right? In CLJ HTTP, we have a lot of other parameters we can add on here. We can say, if the request gets a response that tells us that this thing lives somewhere else, go follow that redirect. I don't want to have to worry about it. Or if it gives us something that is an exceptional response, throw an exception. Don't just give me that error as data. We might even go and sort of define boundary conditions. These are the most redirects I'm willing to follow before you should go and throw an error. None of these describe the data that we're sending. They describe how we're sending the data. When we stop trying to send the data, what we do if it doesn't quite work. But we should not mistake this for an actual implementation of this behavior, right? Data does not have any semantics. There is indirection between these things, and even though we may think we know what these fields mean because they are fairly self-explanatory, maybe they're inverted, right? Maybe it's completely the opposite of what we thought. That is defined elsewhere. We have to actually map this data into something which performs these effects. And so that's why we have functions, right? Functions have semantics. But functions also remove many of the degrees of freedom we would normally have. We cannot reach into a function and pull out a piece of it. We cannot go and reshape a function to perform its actions in a different way. All we can do is wrap our function in another function. We can only increase. And for this reason, we do not want to go and turn our data into a function until the last possible minute, right? Because that goes and just reduces our flexibility down the line. Likewise, we need to recognize that once we turn our data into a function which performs an effect, right? Into an active sort of implementation of the effects we're describing, we are outside the transform phase, right? Because the only way that we can test this function is to make it do a thing, right? And that means that we have to actually sort of test it within a much more complex environment. And so this is why we want the transform phase to be the biggest part of our code, right? This should be the chocolate center, surrounded by this little tiny candy-coated shell, right? And this is what allows us to reason about our code at rest. It's what allows us to use the REPL. It's what allows us to come up with sort of pure functional tests. This is all of the properties that we associate with Clojure, right? The sort of nice development process that we built with this. But the pull and push phases do exist, and we do need to test them. And unfortunately, we can only test them in a place which reproduces the pathological behavior we expect to see in the world. And I am not proud to tell you that often I have concluded that the best way to test something in a facsimile of the real world is to put it in the real world and just see what happens, right? This is all too common because it is incredibly hard to do anything else. And maybe other people will find better success, maybe you'll come up with better techniques for this, but at the end of the day, this is hard enough. We want to keep this as small as possible. We do not want this to own more of our code than it absolutely has to. And I want to just reiterate that a lot of languages or environments or sort of frameworks will go and talk about how they have lots of small processes. You have green threads, you have Erlang's processes, you have Go routines, you have core asyncs routines. And each of these will talk about how there are many small, bite-sized processes talking to each other. And we'll talk about this as if this is this great contribution because now these complex systems can be understood a little bit at a time. And again, that is not true unless these processes are hardened against each other, right? Unless they are not wholly dependent upon each other. Because otherwise they just become this big amorphous mass that we have to understand as a whole, and probably would have been better off just having it be one process. So this has been the meat of the talk, right? How to build a process. But clearly, a single process is not all that we usually have, like especially if we talk about a network. We are then composing these processes together into a system. And this is a big topic, really larger than even a single talk, so I'm just going to kind of do a little survey of some things here. But the first thing that I want to point out is that a process is not valid. You cannot pass a process into something. All we can do is pass in an identifier for that process, or a channel, which is a means of communicating with that process. And in fact, usually, we can use an ID to generate a channel, some means of communicating with. In the simplest systems, when we go and spin up multiple processes, we can simply tell them about each other upon initialization. If we have some sort of shell pipeline that we're setting up, every process upon being created is told, here's how you read, here's how you write, and we just sort of set it up so that they're all talking to each other appropriately, and just let it go, right? But in more complex systems, processes sort of come and go, right? There might be sort of faulty processes, or we might want to go and sort of reshape how the system is sort of shaped. If there's any sort of dynamism, then processes need to be able to find out about each other at runtime. And so in these cases, we go to what is sort of variously called discovery or resolution. Service discovery usually describes us saying, I want to perform a task, who can help me with that? What is the set of things that can help me with that? Resolution is usually taking some sort of abstract identifier and yielding some sort of more concrete identifier. Often that can be used to generate a channel for communication. But of course, in DNS, we don't actually get a single IP address for our domain name, we actually get a set of it. And so this is often used for like geographic load balancing and other sorts of things. And this is true in most of these cases. So usually it is a one-to-many sort of mapping that we have here. But the idea is that we're going and we're taking something which is abstract and can be modified at runtime, such that as things come and go, we can be robust to this, right? We can sort of regenerate and relearn what the current shape of the system is. A related concept is routing. Routing is taking a single channel and then having everybody talk to it and having some process go and distribute the messages that are being sent on that channel across a lot of other backend processes as it sees appropriate. And so we see this a lot in networking, right? This is a term that we sort of talk about a lot there at a bunch of different levels of sort of the IP stack. But a thread pool is a route too, right? There's a queue, we put functions on it, and those functions are shared between a bunch of other threads that will execute those functions. And in fact, most of the concepts you'll see within a distributed system have a corollary within sort of a shared memory, sort of local context. But of course there are differences, right? Going and updating a shared reference means that we know that the data got where it's going. We know that they're at least aware or able to see the thing that we shared with them. We don't know when they're actually going to act on it, but we know that they can see it if they try. When we have an asynchronous, faulty channel of communication, this gets a lot more complicated, right? It's possible that we can get very confused about who's talking. But at the end of the day, communication is a means towards action. It's not what we're actually trying to do, right? The fact that we got back an ACK over TCP saying, oh yeah, I got your message, means it's sitting in a buffer somewhere, not that a process has seen it, not that they've acted on it, not that they'll remember if they crash midway through, like the next few seconds. And so acknowledgement over communication is a means for us to build larger systems which acknowledge the actions that we're trying to perform, right? And in both local and distributed contexts, if we go and sort of throw something over the fence and say, it's your problem now, that's going to end badly. We need to go and create higher order acknowledgements of whatever our application is trying to perform, and only once we get back that acknowledgement do we go and actually, let out our breath and say, okay, good, we're done. We don't have to worry about this anymore. So, again, designing systems, especially distributed systems, is an enormously complex thing. It is well beyond the scope of this talk, or the book that I'm writing, or anything I really hope to have to deal with in my lifetime. But typically when I come up against a topic like this, I try to go and recommend a very canonical book for this. And the closest thing I'm aware of is the book Distributed Algorithms by Nancy Lynch, which is an extremely comprehensive coverage of the theoretical results in distributed systems research. But what it doesn't do, and what no other book I'm aware of does, is give a sort of voice to the intuition that you gain from working on distributed systems for a decade or more. And I wish this book existed, because I'd love to be able to recommend it. I would love to be able to put it in my book as sort of the reference that people should go to look for. If anyone's aware of such a thing, please do share it with me. But I think that if it doesn't exist, then this is a clear vacuum in our industry, right? This should exist, because this is knowledge that people gain, and which is often communicated through sort of gestures and whiteboard diagrams, as opposed to a really formal vocabulary that can translate outside of that one sort of very local context where they're having that conversation. So again, we compose functions to create processes. Processes are the unit that sort of is hardened against its environment, which interacts with its environment, and which is actually reusable on its own in different contexts. And often, we have to go and compose these processes into systems. And that's all I have for you. Thank you.
Okay, so you made an assertion, Zach, near the beginning of the talk, that we need a radically simplified software stack, something like that.
Oh, no, I said in order for us to be able to create systems which are always, are both fast and reliably so, that never go above some sort of threshold, right? You'll see this in some embedded systems, real-time operating systems, which basically eschew all of the stuff that we generally associate with personal computing, right? Because all of that sort of ossified, all those ossified layers mean that we are no longer able to hold the system on our head, which means that we can no longer guarantee that issues won't arise. And so what I was saying is not that we need to radically simplify. I'm saying if for some reason you have to do this, you would have to. But I think that in practice, most people don't. It's not a rabbit hole you should go down. And instead, you should just learn to be more pessimistic.
I see. We have a question from Peter. So you mentioned naming, and that it's one of the hardest things, and that we should study naming.
Mm-hmm.
How does one go about it?
Well, I have a book. No, seriously. The book is called Elements of Clojure, again. The first chapter is available for free. It is called Names. And it is my attempt to go and take the most relevant parts of analytic philosophy and kind of apply them within the context of software. And so that's the best answer I have. The book that was referenced in the previous talk, Data and Reality, is one which I think is truly phenomenal. And it's kind of criminal that it's been ignored. It was published in like the late 70s, and I think has always been a little bit of a thing that a few people will know about but don't actually read. And I think it's maybe out of print, I'm not sure. But if you can find a copy, I recommend it because I think it's a very lucid and practical look at data modeling, which is very closely related to naming. But again, the chapter's free, read it. I make a bunch of different references to different things that I think are sort of ways you can go deeper on that topic. And if you have any thoughts, please do let me know.
And Process and Data and Reality, sorry, is actually available as an audiobook. So if you want to listen to it,
It's an incredibly short book.
It's not
I think
that long.
it's like maybe 120 pages or something, so I wouldn't imagine that long.
All right, so I have another question. So there was a part of a slide, I think it went by too fast, but you were talking about there were 3 things, and one of them was code in motion.
Right. So I was trying to talk about the difference between sort of operational and functional aspects of code. Where we talk about the functions, which is sort of what it does, and operational is kind of how does it work, right? But more generally, the functional stuff is something that we can kind of understand as a self-enclosed bubble, right? Because other people are taking care of what the big scary wolf in front of us. And so and it's useful to separate those for like obvious reasons, right? Because we're bad at thinking about code in motion, because we have lots of things that are happening at the same time, not just like a single sort of linear flow of stuff. But I'm just trying to say that basically, when we're talking about queues, I think specifically that was maybe the slide that you're talking about, I'm saying that queues do not provide separation because actually they make processes conjoined in terms of how they execute, right? This is the file system example. These are all waiting for the other guy because what are they going to do to separate?
Right, and then you said something about the pull phase has to take that into account.
It does, or rather what it has to do if we want our process to be sort of a self-enclosed sort of thing,
Module, yeah.
It needs to define boundary conditions upon what it will take from the world, right? If it waits too long, it has to throw up its arms and say, I'm done with this, and do something else, right? If we don't do that, then it means that basically these things are sort of operating in this sort of interlocked way, and we have to reason about them in tandem, or as a set.
Okay, we have a question from Tyler. Tyler, where are you? Okay, so you're going to have to help me out with this question because I don't know how to ask it. I'm just going to ask it. What descriptions of systems do you know of?
Like languages for systems.
I'm not aware of it. I mean, because I think that it's hard, right? Because a process is not a thing that, like, I think that you can kind of like stab a pin through and say it's a process, right? Like, it's not a butterfly that you can just put up on the wall. You have to go and talk about it in action. And I mean, certainly there are some tools that work with certain parts of this, like Leslie Lampert's TLA goes and talks about certain aspects of the interfaces between them, but it doesn't attempt to talk about what the processes are, right? That's left as an exercise for the implementer. And so I don't know of anything which even attempts to go and create a language for talking about this, which is anything less than just executable code.
Right. Nothing to compose, guarantees of.
I mean, I don't know, right? And I mean, I guess like the problem here, this sort of gets back to the idea, is that like trying to reason out the system as a unified entity is sort of asking for trouble. And so maybe it's better to talk about a process and say, I actually don't know what the other code that I wrote is going to do. So I'm just going to assume the worst. And then on the other side, it's also going to assume the worst. And this creates redundancy in our code, right? It's by putting these things across process boundaries, we're creating a lot of extra work at that edge to make these things sort of separable. But that usually pays off because maybe somebody else goes and starts working on that code. Maybe it's flaky in ways that we didn't anticipate, and we want to not have to go and again load all that sort of runtime into our head just to reason about what's going on. And so, I mean, I guess the ideal that I'm advocating here is let's not talk about the system. Let's talk about processes which don't force us to think about the system. I mean, obviously, like you have to go and be able to chart it out on a whiteboard at some point, but that should be a very high-level exercise as opposed to something which tries to give us holistic guarantees across the entire system.
So you mentioned that a process is either it's never a value. It's always something identifying the process or a channel to talk to that. Or a channel to talk to that process. Does that mean that processes aren't first-class citizens?
They're not first-class values, certainly. It's something which is a sort of amorphous conglomerate of a bunch of different things. So yeah, you can't have like a higher order process. Like you might say that like a Ring web server is kind of like a higher order process because you can kind of plug something in the middle, but you can't like wrap a process around a process. Then it's just two processes talking to each other, right? And so like once you have a process, the only thing you can do is compose it with another process, not like reach into it and sort of, modify anything like this. You're down to like sending messages back and forth and kind of like trying to affect them that way, as opposed to reaching in beside them or doing something to them directly.
So I'm actually out of questions. Do you have any more? All right, someone is asking, have you read Designing for Scalability with Erlang/OTP?
I've read an Erlang book. I think the Pragmatic Programmer book. And I think that OTP is a reasonable example of what I'm talking about, but I have not gone and been paid money to write Erlang, but I know a number of people who have, and I've done, some kind of little toy projects in my own time, and I think that Erlang gives you the tools to create processes which are not in this sort of suicide pact with each other, but it certainly doesn't mandate it. And OTP, the kind of, if anything ever goes wrong, just, shoot yourself in the head and we'll go and create another one of you, is a strategy, right? And that does help you, it's not a bad one. It allows you to sort of not have to explicitly say, here is my error code path. The error code path is always death, right? And so that is actually a greatly simplifying kind of facility there. But it doesn't stop you from creating things which are locked together. It doesn't stop you from having a deadline, right? Like these are all things that can occur there. And it's down to you to make sure that these things don't happen. This is not a guarantee that the runtime can sort of provide for you.
Is there any hope to analytically figure out, like, well, these are the 20, I don't know how many different ways that things can get locked together, and just like put those 20 things in front of it to protect it? On the pull and on the push? And
I don't know. I am constantly surprised by how things can go wrong. Elsewhere in my book, I talk about the fact that I think that what makes a senior engineer is not their mastery of the tools, but rather their ability to predict what the outside world can do to screw things up. It's your understanding of the domain and how complex and screwed up the real world can actually be. And so I do not think that there's a way to enumerate the failure modes. I think that certainly you can enumerate the likely failure modes, but then you have to go and constantly check whether sort of you have to update your priors there and be like, actually, this wasn't possible, but now it is, right? Now we have a new class of user who has a new class of misunderstanding, or we're with a system which is flaky in this new way. And again, you can't impose anything on the outside world, so at best, you have some assumptions you're making there, and you're constantly checking those assumptions to make sure they're still valid.
And like you mentioned before, Erlang has this kind of simplified, like just die model. That just, I guess all errors become the same, it just becomes death.
Well, to some degree, right? I mean, it doesn't stop it from giving you something which, like malicious code which is trying to go and make you do a thing that you didn't intend to do. Like, unless you know that it's bad, you won't die. And so, again, this is a facility, but it doesn't preclude any of the failure modes. It just makes it easier to have a sort of default path you can follow when something goes wrong and you recognize that something went wrong.
So you talked about how a lazy stream is not actually a good full mechanism. Because it's kind of tied together with, could be an infinite stream or something.
Right.
Could you talk about what would be a good full mechanism?
Sure. I mean, so it's not that, if it's a lazy seek, it's bad, right? Because lazy seek is a very overloaded thing, and Clojure, it could actually just refer to operations you haven't, like pure operations you haven't performed on the data structure yet, right? But where that actually represents effects, like the point that I made is that if you have a function, and that function contains effects, you're not actually in the transform phase, right? And so to sort of carry that not from the pull, or sort of not from the push thing, from the pull, if I go and I pass in a lazy sequence, which is performing effects to go and yield data.
Like reading in the lines of a file.
Exactly, right? And if something can go wrong there can be an I/O exception or something like this, then we're not actually in the transform phase, because we can't actually reason about this in isolation, because there is something that someone else can do to screw us up. And so the reason that you don't use a lazy sequence is because it fundamentally shrinks it. So like the M&M is like all candy-coated shell and doesn't kind of get a chocolate thing, right? Like that's not good. That's not what we want.
All right, so Michael asks, so you talked a lot about analytic philosophy and how you're doing a lot of reading in that, but there's another branch of study, of human study, that talks a lot about abstraction, and that's linguistics. Have you looked into linguistics for definitions or other ways of understanding abstraction?
I haven't, actually. I mean, I'm very familiar with semiotics, which is sort of a cousin of all that. But semiotics, it tends to go and kind of talk about these things in the abstract rather than linguistics, which by and large tries to look at real-world examples. And I think probably I would benefit, from this. I mean, I kind of took a very winding path to arrive at my definition of abstraction. And then like a week after I wrote it down, I read an old book by Barbara Liskov, which said it in the first 3 pages, and I was, incredibly embarrassed and annoyed. But like, I don't know. I mean, I think that abstraction, like, unfortunately, again, this is talked about elsewhere, is that we use the same word to talk about some fairly distinct concepts, and it's very easy for us to sort of conflate these different concepts because they're masqueraded behind the same word. And so, I'm happy with my definition because it works for the sort of things that I'm trying to talk about. I'm not claiming it's the only possible definition of abstraction, but I think it's one that works well specifically for software. That's sort of my thing. But if anyone has any books they'd like to suggest in terms of like things in linguistics, whatever, please do let me know. I always love to have more books on the pile.
Could you go over your definition of abstraction one more time?
Sure thing. Yeah. Abstraction is treating things which are different as equivalent. Right? So we're saying that there are differences, right? The tree has leaves, doesn't have leaves. The leaves are green or red, but that doesn't fundamentally change what the thing is for us. And so at the end of the day, it's really about identity, and most data modeling is about identity. This is what data in reality talks about a lot, which is what are the things that we're able to ignore and what are the things that don't, right? If a baseball team loses a player and gains a different one, is it the same team or not? If they move to a different stadium, is it the same team or not? And the answer to this depends on what sort of problem you're trying to solve. If you're trying to predict the outcome of a game, it is a different team if a player is injured or a player is traded, right? If you're selling tickets to games, you don't really care. And so these are not things that you can talk about in the abstract, right? You have to actually go and ground them in some sort of concrete context and then say, this is good or this is bad, but also, here's what would make it not good, right? Or not bad, right? Here's what would change here that would actually force me to reevaluate whether or not this is an effective abstraction. And we're like well past the end of this. I'm happy to go and take more questions in the hallway, but thank you again.
Yeah. I think we are over time. 5 minutes left on the break. On the clock? Oh, we're not over time?
Oh, that's not possible.
Look at that. Yeah, no, we do have 4 minutes. Any more questions? Why not? We have plenty of time.
Yeah.
So yeah, so you, in the transform phase, you had 3 different things it could do.
Mm-hmm.
Accrete, reduce, and reshape.
Mm-hmm.
Do you think that's it? Is that?
I think so. I mean, they're pretty broad, right? I mean, either you have more data or less data or the same amount of data, just different, right? I mean, short of an identity function, which, like, you know, I think that's pretty exhaustive.
Nothing.
Yes, exactly. You can do nothing with data.
Right, so is reduce, you said that one was an abstraction because, you know, like your example of your summing, you're making all of the sequences of numbers that sum to the same number equivalent.
Yes.
Is that the only one that's abstraction, the reduction?
Yeah, I mean, because accretion is going and saying we need more data, right? It's not lossy. It's going and actually capturing important new qualities to all the data. It's lossless, right? And reshaping is not abstraction because, again, you're not treating things which are different as different. What you're doing is, or sorry, different as the same. What you're saying is, I actually want to take close attention to how this data is being represented, and I want to change that. And so, in both the accretion and the reshaping, you're going and saying, there are things here that I care about very much. And in the reduction, you're saying, there are things here I do not care about.
All right, so I'm just going to keep asking questions because I have yeah.
Yeah, I got a question. Is that,
Yes.
so at some point, there's this trade-off, right, between abstraction and performance and being able to hold stuff in your head and complication. That's kind of one of the gist I got from you. Is it just a matter of scaling out your unit of what you have to hold in your head? So we have folks like working on like the Linux kernel, and we have all these experts that are in their small particular domain. There's not one person, well maybe Linux, but there's not really one person that I would expect to hold that all in their head.
Mm-hmm.
So is it really just a matter of scaling it out to a small enough unit to where somebody, a specialist, can hold it in their head and can then communicate with other specialists? So that way you don't lose. So I mean, in that case, it's like there's this natural tension between performance and simplicity, I guess, and you're trying to, over time, you have the system that blows up because you're trying to manage all these different, like you said, the file system and everything else blows up in the complexity for a reason, for all these other things you talked about. So it just seems like maybe there's another side of this, whereas we could scale it out on the human side, and you could actually, I mean, I could very simply just look at my small piece of that puzzle, and I can communicate with the other experts in the field.
Well, you can as long as you're not wholly dependent on what they're doing for you, in which case you can't ignore them, right?
Sure.
Like the file system, if you need what's in the file to do something, and you have requirements that the file system perform anywhere near its sort of theoretical peak in terms of throughput or latency, then you care a great deal how that works, and you can't possibly ignore it, right? The only way that you get to ignore that is when you say, actually, if like we just pretend it's like, 1970 and we have tape decks, and like that would be fast enough for me, then like, yeah, sure, go wild, like ignore that, right? And SSDs are a great boon there because they give us a much simpler sort of random access model to think about in that sort of specific domain. But I'll sort of push back a little bit on, I think, the premise of your original question, because the modules in a long-lasting system aren't what last, it's the interfaces, right? The interfaces are what ossify, the interfaces are what are lasting, and the modules themselves that sit on either side can get freely swapped out, right? And so I would expect that at the high level of Linux, there are at least a handful of people who understand all the interfaces between all the different pieces, even if they don't necessarily understand exactly how, the sort of innards of that module work. And they probably spend a great deal of time thinking very carefully about what is allowed to be in or not in that interface, right? But to your point, yes, often, like the way that we get faster performance is by adding something to an interface that allows us to go and rely on some sort of implementation detail that like a new piece of hardware or a new sort of approach affords us. And that's a super tricky thing, right? Because that makes us less general, and that kind of ties us a little bit more closely into the specifics of how it's being done now versus how we might want to do it in the future. And that's sort of where the trade-off is. It's basically how rich do we allow our interfaces to be, or versus like how general do we want them to be. And there's no one good answer to that. And again, I talk about this more in the talks I've given in the chapter I've written on abstraction. I'd be happy to sort of, if you read that or watch the video or whatever, and have sort of further questions there, I'm happy to go into that.
When can I buy your book? When's your book coming out?
So It is available, right, on GitHub. You can buy it. You can buy an incomplete copy. And since I did that 2 years ago, and I'm incredibly grateful that they've been this patient. This talk here represents the material for the final chapter. And I haven't written it all down yet. I hope to do so in the near future and sort of get that out there. And at which point, that will be a mostly complete first draft. Once that's done, I'm going to reserve an unlimited amount of time to go and tinker with it, because at that point I feel like I've kind of given what people paid for. But you know, it's each chapter I've written, I've gone and I've rewritten and I've sort of played around with, and so I expect I'll do the same here. And I would be surprised if it's anything resembling a final draft before the end of this year.
How many people have bought the book? How many
Thank
people
you.
have read the book? How many people read the first free chapter? I have one final question.
Sure.
So, you used some examples that were like Unix utilities, like cat and grep. And those are surprisingly long-lasting. Like, they've been around a while. Is there any hope that we could find another set of operators like that that are, you know, general and useful enough that we'd be using them in 50 years?
Well, I mean, I guess you could argue that the list, the family of operators also fit that, in fact, are longer lived than that, depending on whether you talk about sort of common Lisp or like the Lisps, right? But, I mean, again, so like, consoles are no longer the preferred representation of data, right? They're a very general form of data, but they don't map very clearly on how the underlying hardware works. They require us to jump around memory far too often, and so everything in Clojure, except for code representations, uses chunked, like, sort of sequences, right? And so, and likewise, you can say, gosh, grep is super, you know, general, because it says everything's text. Even, you know, if it's just like raw binary, maybe it's text. And, I mean, yes, but, like, we're giving up a lot of freedom by going and sort of shackling ourselves to that sort of foundational assumption, right? Notably, we can only deal with flat data. We can't deal with nested data, right? Unless you go and use a command line tool like JQ, which is meant to sort of slightly help us with that, but it still is very painful, right?
And some kind of fixed point like the list or the list.
Right, but you know, the point is that like these sorts of things, like they might be mathematically eternal, but they're not eternal in their utility because that's a moving target. And so I think that, you know, we can be very grateful that the guys who did like the original Unix were so prescient in creating these things that are so flexible. But I think that the fact that something's lasted for a long time doesn't mean that it's retained its value over all that time. It means it's retained some value, right? And I think that having something be long-lived just for the sake of being able to say this is long-lived is not a goal, right? The goal is for it to be like retain its value for a long time, and that's a much trickier proposition as you can predict the future.